class for Module 9, which is about benzene and aromaticity, is Class 21. Let's look through the Class 21 handout and fill in any blanks that we have there. I don't think we have too many blanks, actually, in this handout. On page 1, I talk about why benzene is considered a conjugated pi system, and I show you the resonance of benzene and how you could represent a benzene derivative two different ways, depending on which resonance structure you use. At the bottom of page 1, I also have some nomenclature about ortho, meta, para. Page 2, memorize the name for toluene, aniline, phenol, and nitrobenzene. Know the name and the structures, because those are the parent now. We don't say, for instance, for the second molecule, we don't call it 1-fluoro-3-methyl benzene. If it has a methyl group on a benzene, the parent becomes toluene, and we call it here now 3-fluorotoluene or meta-fluorotoluene. We talked a little bit about the acidity of phenols and how you're always expected to know how to determine the site of equilibrium based on the pKa table. Phenols have a lower pKa than regular alcohols because of... I don't think I talked about that. Okay. Why is phenol a pKa of 10 when a regular alcohol is a pKa of 15.5? Here we have phenol. And a regular alcohol that's similar, maybe could look like this. Messed up. Okay, no benzene ring. Just a regular secondary alcohol. This has a pKa of 15.5, a regular alcohol. Because when we make the conjugate base, it's all about, again, the base. The more stable the conjugate base, the more acidic the acid it came from. The conjugate base of this phenol looks like this, and I'm going to draw the lone pairs, negative, versus the cyclohexanol conjugate base looks like that. Okay? I think everyone could tell that we have resonance. And you could put the charge right on that carbon there. And we have this. Now it's not the major resonance contributor because we have the negative charge on the carbon. Okay, negative. But it still adds to the stability. The next set of arrows, like this. Okay, I'm going to go down this way. Okay, can we finish the rest of this resonance? Let's take this lone pair, make a double bond, put the lone pair on that carbon. You notice that the charge skips the carbon as it goes around the ring. So here's your negative charge up there. What else do we have? This and this. Okay. There is actually one more. Technically, we have this. We can see how... I'll draw it out. The double bonds are now shifted in the ring. They shifted... I was going to say clockwise, but it doesn't matter which way it shifts, as long as they shift. So take a look at these two right here. This one and that one. Those are different contributors. Very resonance stabilized. So for this one, the conjugate base is resonance stabilized, which means that this is the stronger acid. The conjugate base here has no resonance. that charge is stuck on oxygen and it's less stable. No resonance, less stable, conjugate base. Okay. All right. And so that's why phenol has a pKa of 10, which is much lower than 15.5. Page 3, we take a look at more groups, electron withdrawing and electron donating. Do not forget that methyl is electron donating. Okay, and so it's a very, very slight, but when we have phenol, this is on the top of page 3, just a plain old phenol, they call it 9.95, but when we put a electron donating group, it goes up. So here we have CH3, slightly up, but it's still up. So it becomes less acidic because donation is bad to stabilize anions, right? You want withdrawing, right? How are you going to stabilize this anion when you're pumping in more electrons into the ring like that we have here? On the other hand, and we saw this on the in the class, on the other hand, if you have a nitro group, and I'm not going to draw out the resonance structures, we did this in class. Okay, understand why this is more acidic. So this has a pKa of, wow, 7.15. Okay, more acidic. This is an electron withdrawing group, and the alkyl groups are electron donating. There is the effect of those two types of groups. Page 4, at the top, we discuss Kekule, and his Kekule structures, which were close, right? It's what we draw, basically, except that it wasn't known at that point that the carbon-carbon bonds were all equal in length. That came, or the explanation came, with Linus Pauling in about 60 years later. Nothing else on page 4, no blanks there. Page 5, nothing. We talk about frost circles a bit later, actually in the next lecture, lecture 22. The difference between the 6-membered ring benzene and the 8-membered ring stop sign, cyclooctatetrene. That molecule, the stop sign, has a little bit of stabilization, but it's not as much as benzene. So benzene is special. It has this, I call it aromaticity stabilization. And to figure out aromaticity, we have the Huckle rules, and then we had a couple of examples. We did the cyclooctatetrene. We did the, we call it 10-annuline. This is the top of page 7. And we have here, next we have 5 molecules. I added a 5th one, the 5-membered ring with a negative charge, and that's the one we actually went over in class. The other molecules on page 7 of class 21 handout, we went over in class 22, so I'm not going to do it here on the video. That's already done in class 22. Same thing with the frost circle on page 8. I talked about that in class 22. Okay, this is a short video, but I also want to give, as a little bit of extra help, some helpful hints. And so we'll label this helpful hints. Because, there are exceptions to these, not exceptions, but some subtleties to these rules. For instance, one of the rules for Huckle said the molecule has to be flat. Well, how do we know it's flat? We don't know it's flat. We have to determine whether it's beneficial, whether the molecule will conform to be flat because it gives it aromaticity. But if it gives it anti-aromaticity, then it will try to become unflat. It's the same idea as the molecule, quote unquote, choosing between staggered and eclipse. It's analogous to the 6-membered ring choosing to be a chair conformation versus a different conformation on chair, flat, basically. So the molecule can sense, where is the stress or the strain, and it could go away from that strain until it finds the most stable conformation. We have some of that happening here as well. So let me give you a couple of definitive rules. Let's call them A, B, C, D. For A, always 5, 4, and 3 membered rings are considered flat. Are flat enough or cannot become unflat to break any conjugation. But I'm going to put here are considered flat. Okay, 3 points make up a plane, so three atoms will always be flat relative to each other. The 4-membered ring, right? The 4-membered ring, you could let me just draw it. Actually, you can twist a little bit, this corner up, but it's not going to be unflat enough to break any overlap. What are we actually looking at? We're looking at the overlap of the p orbitals, okay? And if we don't want overlap because it leads to anti-aromaticity, the molecule will become unflat, but these rings, 5, 4, and 3, are too small to sufficiently become unflat. Okay, they're too tight of a ring. And we have the 5-membered ring as well. We're going to consider those rings also as flat. We cannot bend them out of plane enough to get the p orbitals misaligned. So that's really the main point. They're small and can't bend enough to sort of break the alignment of p orbitals. Now that could be a good thing or it could be a bad thing, right? Depends on the Huckel number. If the Huckel number tells me it's anti-aromatic, that's a bad thing. I really wish I could make this unflat. But for the small rings, you cannot. B. Carbocations or carbocation carbons are always sp2. So there's no choosing there. Always sp2. So for instance, this molecule here, are you making your list of molecules that are aromatic, non-aromatic, and anti-aromatic? That carbon there has to be sp2. Well, nuts. The molecule's flat, again, because of this rule here. It's all atoms are sp2, but we have a non-Huckel number. We have 4 pi electrons. Anti-aromatic. But that's not the point of this rule that I'm saying now. I'm saying that carbocation carbons are always sp2, which is good. There's no choosing. You don't have to decide if it's good or bad. It's always sp2. Now, I didn't go over this in class, but also boron with 3 bonds, with 3 single bonds, is always sp2. So great. If you have a ring, it could be aromatic if it has boron, because boron is sp2. It cannot choose to be sp3. It has to be sp2. And so, for instance, now, again, man, this 5-membered ring is flat. Let me give you another example, actually. Well, let me finish this thought, because this is also anti-aromatic. Anti-aromatic, anti-aromatic. Right? All the atoms are sp2, we only have 4 pi electrons, and the molecule is flat. Let me give you a good case where boron, it's good that boron is sp2. How about this, right? Boron with 3 single bonds. Again, this atom is sp2, great, I think. It has 2 pi electrons. Okay, it is great. Because 2 pi electrons is a Huckel number, flat, for sure. All 3 atoms were sp2, aromatic. Okay, so here are some examples of molecules with boron, and we have to choose between aromatic or anti-aromatic. Letter C, I think this might be the last. So when do you have to worry about choosing? I said, and I think I typed it out in the notes. Yeah, it's a weird rule. If you have a atom with 4 balloons, so in Organic Chemistry 1 we knew this as sp3, but also has a lone pair. Then the molecule can conform to be sp2 and put that lone pair in a p orbital. So let me show you some examples. It's basically going to be the carbon anions that are these examples. I didn't finish my thought. If an atom with 4 balloons, sp3, but also has a lone pair, it will become the atom. It will become sp2 if beneficial, if it makes it aromatic. But yeah, I'll write that down. If it makes molecule aromatic. If it makes it, by the way, if it makes it anti-aromatic, then it's better to be sp3 and become non-aromatic than to be sp2 and become anti-aromatic. So I'm going to give you a couple molecules where you can choose whether that atom is sp2 or sp3. And here's one of them. Okay. I want to remind you that you are responsible to draw the lone pairs. The person drawing the structure, whether it's a journal article or a textbook or notes, it's not necessary to draw the lone pair. Only I draw the lone pairs mainly when I do mechanism. It's necessary to draw a charge to tell them that that's a carbanion, and the students should know that there's one lone pair. So know who has lone pairs. So this is one example where it looks sp3, but if I make it sp2, the lone pair will be part of the pi system. Okay? And so this is aromatic. Now, and 6 pi electrons. 6 pi electrons. Let me give you another example. We did talk about this in class. What about this? The oxygen atom. That's 4 balloons for sure, because we know this is true. Okay, I'm just reading my note, make sure it fits. 4 balloons. In Organic Chemistry 1, we would call this sp3, but here, if it's beneficial and it's aromatic when it becomes sp2, then this will be sp2. And yes, it will be sp2. We drew the orbitals actually in class, so I'm not going to try to prove again that we have 6 pi electrons, and this is aromatic. Okay, what that does imply, though, is that this one is in a p, so that kicks us up from 4 to 6, but this one cannot be in a p because we only have one p orbital, and each orbital can hold a maximum of only 2 electrons. This stays, or not stays, but this is in an sp2 orbital. Okay, give me 1 second. Okay, so where are your places where you have to choose? Carbanion, oxygen, nitrogen. Okay, I'll talk about this in the next video, but nitrogen. Okay, now we've seen this example before where we have this 5-membered ring, and it would be great to have a lone pair be included in the pi system. So this is another example, and this is aromatic. 6 pi electrons, aromatic. Now, this is just coincidence that they're all aromatic. There are cases where you want to keep it as sp3, and, here, I'll show you a case for that. How about a 7-membered ring? Give me 1 second. No, I want to make it flat. I want to force you to make it flat. So let's do a 3-membered ring, and there's your negative. So we have a lone pair right there. But you notice, if the carbanion is sp2, I will get kicked up to only 4 pi electrons, from 2 to 4. That's anti-aromatic. Anti. That's sad. So instead of making sp2, we will stay. Instead, stay at sp3 and make it non-aromatic. Okay, so this is one of the cases where we don't want that carbon to be sp2 because it would make us anti-aromatic. Stay at sp3 and keep it non-aromatic. And we saw this example in class, non-aromatic. Okay. Think about those rules, or not rules, hints, A, B, and C. It's to help you not overthink things, right? Not every atom can choose to become sp2 if sp3. It has to be beneficial, and again, it has to be sp3 at the beginning, or according to Organic Chemistry 1. Now, here we have some examples of oxygen and nitrogen. There are oxygen and nitrogen containing molecules where, again, you cannot choose. Let me put another example actually right here. I'm looking at part B. Carbocations, always sp2. Boron, always sp2. Atoms with double bond, always sp2. sp2. Look at this nitrogen here. Double bond. And we have a lone pair. That nitrogen has to be sp2. Okay, it's not one of these cases down here. Okay, so this is sp2, and if that's sp2, the p orbital already is occupied, making this pi bond. So automatically, this orbital that has the lone pair is an sp2 orbital. It's different for these others, right? This lone pair here is part of the pi system, p. So I put the 2 lobes to represent the p. Same thing here, p. But the other lone pair is in an sp2. Okay, it's a little bit messy. Go ahead and copy this. This would be a great actual, like, note card or 1-page study sheet, because it simplifies when do you have to choose between sp2 and sp3. It's very limited, right? It's very limited. Everything else, or all the other examples, sp2, carbocation, sp2, boron, sp2, an atom with a double bond. Okay. Hopefully these hints help a little bit. It will take practice. Okay. The last video will be class 22. It's coming up. But I think this is all I want to say for the class 21 handout.